Yes, sir. Sir,
Yes.
you can continue, sir.
Yeah. Yes. Okay. So welcome back. Yeah. So yeah. Any doubts? Any comments from the previous session? Then we'll move to the next. Okay. So we'll see some other families of this RNA and what are the problems, and then we'll go to see some applications. Okay. In this session. Is anyone having comments, or you are there already? So you are joining one by one. Is anyone having any difficulty? Any difficulties? Any problems, doubts? Is it okay? Shall we move?
Yeah, participants, please kindly respond. Yeah.
Hello, sir.
Sir, continue, please.
Okay.
Hello, sir.
Yes, yes.
Sir, like these are the we are putting the RNN layer over here. So how many neurons we need to put in that RNN? Will it be dependent on the previous layer? Like I am like doing this character level language modeling,
Yes.
and
This in this here you mean this three.
yes,
What are these three hidden layers, right? Three input. It means this input is fixed, right? Four.
input is
Hidden.
fixed for yes.
So
Then
you
I am
can make it
using this
five or
RNN
six,
layer.
whatever. In certain layers. Yes.
Yeah, then I am using that RNN layer. So in that RNN layer means selection of neurons. How many neurons I need to use? Will it depend on that input layer?
Okay. See, when it's like your multi-layer perceptrons. Okay. So let us consider a simple multi-layer perceptron, a neural network. You give an input, you have an input sequence. Okay. Input 10-dimensional feature vector, x1 to x10. Right? x1 to x10. And then you want to get some output. Output is, for example, it could be one category, or it could be car or human or something. So how many neurons you want in the hidden layer? Where it matters? How will you choose?
Like 10 features I have.
Yes. Let's consider a simple neural network. Okay, multi-layer perceptrons. You have 10 input features and one output. And then in the hidden layers, let us consider a single hidden layer. One hidden layer, and then how many hidden nodes you will place in this hidden layer.
So that is a hyperparameter. So I will like try and error.
Yes. So same thing here.
Okay.
So this is a neural network. Okay. At the core, it is a neural network only.
In this like RNN, it is unrolling. So I might think that it might play some role with that unrolling kind of thing.
See, whatever in hidden layers, the number of nodes, neurons in the hidden layer, it will be same in every state. Whenever you unroll, it will be same everywhere. So if you
Okay.
consider, for example, 3, so it will be 3 everywhere. If you consider 4, it will be 4 everywhere.
Okay. So each neuron will unroll.
Yes, each neurons are actually unrolled every state.
Okay. Okay. Thank you, sir.
Yes. Yeah. Any other questions? Instead of 3 in this hidden layer, I could make it 5. I could make it 7. Okay. And we have to see that with which number it actually works. Any other doubts? You consider that this is a multi-layer perceptron, okay? Simple neural network. How do you function? How do you work? So it is same thing. It's actually just rolling again, repeating again and again. Only Difference is that the output you receive after this activation function, this is considered another set of input in that next state, in the next level. That's it. So which actually provides the previous information, okay? Previous or context information of the previous. Okay, so you can say that if you are considering the third word, second word information will be more. Then first word information is there already here. It will be a little small portions will be there, but these are all combined and connected, combined, and these are coming here. Fine. Anyone having any doubts?
No, sir. We can continue.
Okay, fine. So if we just say that, I just repeat this slide. Yeah. So RNN, it will be like what you can do. So you have this simple multi-layer partial neural network. You have just, for example, you give an image, you do some classifications like your CNN. With RNN, you can do one to many output, one input, many output, many input, one output, many input, many output, and many to many. Okay, these are also what we mean. So we give only one input, image. Okay, so for example, it's an image captioning. We give an image, and this image, it extracts some features, and then from those features, we understand that, okay, what are the objects in this image. So that's called image captioning. Means we want to find some words of this image. Okay, so for example, it's a straw hat. Okay, so we have to find out these different words. Okay, so from this we extract from this image input is features. Okay, input is image. From this image we find out using some CNN, extract some features, and these features are fed into this RNN, and then we use this multi-layer person, this RNN layer. So after this Y1 we get some labels, okay, some results, some one word, and this word is actually influenced with these features again, and we get some another word, okay, that is called one to many. So we, from this one image, we can find multiple words from which actually describe this image, which is called, this application is called image captioning. So from one input, one set of features, okay, so we actually get output. In this, you see that in this every other states, next steps onwards, you do not have this x. Okay, x part is 0. Only you are considering these features. This the first information. Okay, that is propagated, and you are getting the results. And then finally, you have this loss functions that we will discuss. For many to one, you have a set of words in a sentence, and from this sentence, you want to find a sentiment. It is positive or negative. Okay, so this you will also get outcome, but these outcomes you ignore, you do not consider them. So finally you just consider the final level outcome, whether it is a positive or negative. Okay, those outcomes you do not consider. In machine translations we use many to one and one to many. Okay, so that means if I'm saying a sentence in English, you want to convert into Hindi. So you have a sentence, English sentence, a set of words. So from this set of words, I have to find out the gist, okay, understanding of this word, sentence. What does it mean? what actually I wanted to say. That means it will find out the meaning of the sentence. And then once you find out the meaning of the sentence, this sentence, if I am translating into another language in Hindi, so what will be the sequence of words? In Hindi, what are the set of words I will produce? So it is many to many, many to one, and one to many. Okay, and then you will have video classifications, like when you have many to many, means you give input, okay, and then from input you generate the output, and then that output is also depend it gives as a it uses as it is used as input, and then it gives you another results. Okay, so for example, if you have a sequence of frames in videos, okay, that like I was saying, this, for example, this autonomous video driving, okay, so vehicle driving, so you have a set of frames. Each frame actually you may use from one frame you get some results, okay, and that result you actually consider for the next frame as well. Okay, so next frame you have a different input, and this input, and you got some results in the previous frame. So previous frame information and this present frame information both are combined to get a next frame, some new results. So that is called many to many. So these are different possibilities with recurrent neural network. Okay, this you can use this output of this recurrent neural network in various ways. Is it okay? Fine. If we move like this, so as we understand that whenever we want to do some is in multi-layer perceptrons, what we are doing, how we train these weights, we get the loss functions, and from those loss functions, we back propagate and adjust the weights. Okay, so if you are having these outcomes, so for each outcomes, you will get the loss functions. Okay, if it is a single outcome, you will finally get outcome. You will have the loss function at the last level. Okay, in the previous, you will not get any loss. So you will have, so like this. Okay, so if you have many to one, you will have loss here. So if you want to train a recurrent neural network, so first you will be doing, you will set initialize with some random weights, okay, some values initially, a random numbers, and those numbers will be, you will get the results, okay, just like forward propagations, forward pass, you will get the results, okay, you will have this y functions outcome, you make the loss, and this loss actually will be uh, this loss will adjust all the weights in the backward process. These are done using back propagation. In back propagation, you use gradient functions. Okay, so you are using actually, for example, if you studied this multi-layer perceptron, you had this mean squared error, and that you are using this squared error. Okay, so this you are using this gradient, sorry, the loss functions, and this whatever is the loss, you find out this loss with respect to each weights. Okay, so the weights, and then you see the weight modifications, and then you modify. Okay, so if you have this cell, you have this HT and XT, these are all stacked. Okay, 1 after 4 plus 3, 7. This is a total 7, and then you are using a 10h function, the activation functions, and you get the HT. Okay, so now if you want to do some back propagation, so you have this, you generate the loss functions, and this loss functions loss values will be propagated. Okay, so using this backward flow. Okay, so like you have to compute the gradient information of this activation functions, right? You remember in this, when you consider this backpropagation in multi-layer perceptrons, you actually use this gradient operations. Okay? So that's why this activation functions you have to choose in this way that you can do this gradient. Okay, you can find out the gradient operations. So if you have a set of 3 or 4 rows of frames, for example, if it's video classification, okay, 4 different frames are there: first frame, second frame, third frame, fourth frame, and this first frames actually gives you this results, and like this, and then you have the total error, and then finally these errors are actually adjusted. So adjustment will be done in all these states. Okay, it will not be done in a single one. So it will be as it in forward pass, it was done like you do the calculation, you move to the second level, and then you do this calculation, you move to the third level, like this. So a backward pass also will be done in the same, okay, in this gradient operations. So we are not going to do this mathematics of this, how this gradient operations are done. Okay, so these are as with this multi-layer perceptrons, and this you can follow other rules. Okay, the concept is whatever you do in the forward pass, the gradient flow will be done in the same way in this backward flow. Now the problem will be if you have, because you will have several states, okay, many states, many frames. See, if you are having many frames and you are considering the gradient operations, okay, so when you are having some you calculate the gradient operations, sometimes some values will be large. Okay, so what will happen if you consider the gradient values? So it will actually you multiply, okay, with those large numbers again and again. Okay, so large numbers again and again, and it will be huge number. So that actually you cannot store, okay, and it will not, you cannot compute, you cannot do the processing as well. Okay, so this is one problem that is called explosion of gradients. Okay, so when the number value is large and you are doing this gradient operations for this backward processing, backward propagation, so if the number is large, so you are actually multiplying this large numbers, because in this gradient operation, if you remember, these are all multiplication, right? Okay, so these are all when just if you do not remember, just you consider that in this gradient operations, we do this multiplications of some a set of numbers, okay, inputs, whatever are actually connected. So when some values are large and this you are processing, okay, in for example 5 or 6 states, so it will be multiplied. Okay, the same number, the large numbers will be multiplied. So that means it will be an explosion. Similarly, if the number is very small, 0.002 or 0.003, so or less, or 0.00004050, something like this, small numbers will appear, okay, in the gradient operation. Then, if you are doing this back propagation from one state to another state, then those multiplication factors will be there. And then when you multiply with the small numbers, then this total number is actually coming very less. So this is called gradient vanishing. Okay, so gradient factor actually is almost lost. Okay, so you are not able to find out store this gradient because these are multiplied repeatedly in each state. Okay, so if it is a large number, it is explosion. If it is a small number, it is vanishing. So we have to do something. Okay, so these are called gradient explosion, exploding gradients, and it is called vanishing gradients. So for when the large numbers are actually coming, so we can say that, okay, so I cannot have large numbers, so I can say that, okay, I can clip it like more than 50. If it is there, then I will keep it 50. Okay, so like this. So for example, you have this ReLU, okay, ReLU functions. If it is negative, always it will be 0. Okay, so something like this. Okay, so like if you have some small numbers, then you can keep it like this, fix a value, and then you ignore the other parts terms. Similarly, if you have some large numbers, so more than if fix a value, that 50 or 100, and after that, if the value is more, then you can ignore that other parts. Okay, the part of that number. So that is called gradient fitting. And another way you can actually use this backpropagation, that instead of combining all these loss functions together, so if you have a series and you instead of considering all these loss together, what you do it in a group, okay, set of blocks, either 5 blocks together. Okay, so in a 5 blocks, you consider the loss and then you modify. And then again, you consider 5 blocks and then you modify. Like that also it is possible. That is called truncated backpropagation through time. Okay, so instead of this full process, full unrolling, I will just consider a set of blocks and then I'll find out the loss and then we'll adjust. Okay, so instead of this full block, I'll just modify in this a part and then I adjust. So this is more or less this recurrent neural network. Okay, so it works like your multi-layer perceptron. You have this forward pass, backward pass, and this backward pass, you are doing this gradient descent algorithms to adjust these weights. So in gradient descents, sometimes there will be explosion, sometimes there will be vanishing factors. So how actually to control? There are different family. There is a family of RNNs. Okay? So many variations of RNNs are done. So RNN, as you understand, is actually keeps the ordering of the sequence, which helps to have the context of the sequence and you get good results. There you have stacked RNN, bidirectional RNNs, which are coming from RNNs. And if we modify the cell structure of this RNN, so that is called LSTM GRE. In RNN, if we just consider a single RNN and we make some wrapper, okay, so RNN, one RNN to another RNN, that's called stack RNN bidirectional. And if you want to change the architecture in the RNNs itself, in the cell, there actually you have these two members, LSTM and GRE, long short-term memory and weighted recurrent. So we'll see all this one by one. So let us consider this bidirectional RNN. Bidirectional RNN, what it does. So for example, you have a set of words, okay, input, and then you get the results, okay. In a if you use the RNN, one set of RNN, you get this results, okay, like HT minus 1, HT, and HT plus 1. Okay? And then this bidirectional means this is a forward, means you consider like, for example, this is computer. Maybe I can write a big sentence that I am going to school. Okay, so here I am going. Okay, so like this, to school, 5 steps. Okay, so here it is processed, means the first recurrent neural network, it is processed like this in the ordering which comes from the forward. I am like this. This another layer, another RNN can work from the future, means going to school, from the school, then to. So I will consider from this backward side. Okay, so that actually this RNN will consider from the last. Okay, that is called bidirectional. One will use the past informations from the past to the future. Another RNN will move from the future to past. Okay, so both informations are processed and these are actually combined together. Okay, so here one RNA which is actually coming from this forward. Okay, so from this past to future, that's actually the whatever we have discussed already. This RNA is a simple RNA, and then another RNA which actually takes from the uh, last words. Okay, last word. So then you will have this last word. This will be considered as the first word, and then for then each of these words you will have the previous information and the past information and the future information. Okay, so this forward layer actually considered the previous history information, and backward layer is actually giving you the future information. Okay, future context. So now we can combine this future and past both, okay, together. So this actually you are combining with an weight. So this, for example, if you consider this layer, this architecture, this part, you have this from this. This is from forward, this is from backward, and it's from the same word. And then finally, what we are doing, we combine these two output together with some matrix weights. Okay, so W4 and W6, and you get the final output. Okay, bidirectional RNAs are used when our outputs depend not only on the previous values but also on the future values. In such cases, we run the model in both the directions simultaneously, both contributing to the final outputs. Okay, so for example, I can give you one example like if you write a word, handwritten word. So you'll see that if I write a word, if I do not understand, for example, simple character wise, it's a let us consider that is a cursive handwritten A B C. I'm writing like in cursive. Okay, means all these characters are connected, and then B. Okay, so when I'm writing this B is connected with A. Okay, so I'm using this A to B information. How this information scopes are processed. Similarly, if I also want to know that I do not understand this how actually it could be B or it could be L. Okay, so it is A after A it could be L also. Okay, A instead of B I can say that is L. But if I just process from the end, so you will say that okay it is C. That means this part will be combined with this B. Okay, so this will be a B. So from future also, if I see from this back side, then it will be more clear. Okay, so what actually I wanted to write. So both informations are combined together to get the final level. This is bidirectional. In stacked RNN, okay, so it's a forward. Okay, so you can use usually people do not use bidirectional, but it's a you have one RNN. So you have this set of words like I am going to school. You process them using some whatever we discuss RNN, and then you get the results. And these results you use another RNN. You can use another RNN. Okay, so that whatever output you will have, so you are using it's like your deep models, convolution models. Okay, multi-layer perceptrons. You instead of this using another RNN, another RNN. Okay, so which are actually doing the same thing. You have this input and this output. Then output of the previous state is actually combined. Okay, this is a one RNN. This is another RNN. Okay? You can use separate stacks of RNN. Okay, in stacked RNN, each RNN layers outputs a sequence of vectors which will be used as an input to a subsequent RNN layers. Okay, so each RNN is actually giving you an output. These outputs are considered as input to another RNN. Okay? This hierarchy of hidden layers enable more complex representation of our time series data, capturing information at different scales, thus allowing the model to make more robust decisions in case of more complex problems. So that actually helps you this back RNN. So if you are using this, so you have when you are using a single RNN, so maybe the past information is more important than this previous one. But when you are combining these 2, 3 RNN stack, so maybe those informations will be given more weights. Okay, so that actually this context informations are important and you get better results. Is it okay? Bidirectional and stacked RNN? Any comments? Do you have any doubts? Any doubts? Is it okay? Do you follow?
Yes, sir, you can, sir.
Sorry, is it okay?
Yes, sir, it is okay, sir. Yeah, it is okay, sir.
Okay, thank you. Okay, so let's move.
Thank you, sir.
So you have those where, yeah, you write something, okay? So because see, this is the problem in this virtual online mode, okay, this workshops or events, because I do not see your face. I'm just talking in front of my laptop. So if you do not show your emotions, expressions, I will not understand. Okay, so whether you are really understanding or is there any difficulties, you have to say. Because if there is no interactions, it will be difficult to know that, okay, whether I really you understood or not. Otherwise, I can, okay, I don't have any problem. But I want everyone should be involved. Okay, so means I do not want to go with lots of slides. Means whatever I just cover, everyone should understand. Okay, so there are actually another set of families of RNNs which actually modify those RNN cells, yes, with a different combination. So, but basic architecture remains same. So RNN is that I have said RNN, you have this bidirectional and then stack. And then you can also make this RNN, stack RNN, you can also use bidirectional. Even in this bidirectional also, you can use this stack sometimes. Okay, so these are actually you can do with this all this combination permutations, whatever possible. And then in this LSTM, okay, so it tries to solve the problem with those exploding or vanishing gradient. Okay, so those were not considered in properly in RNA. So these are considered using some changes, modifications in the cell. So which are actually we use 4 different gates. Okay, so one you will discuss this input gate, output gate, forget gate. Okay, so these are the different gates. We consider that which information we will process, which information we do not remember, we do not need to remember. Okay, so those kinds of informations gates actually we use small. It is more complex. Okay, this LSTM here is a little more complex than this RNA because that more advanced, more little complex, so that it actually does not process all information. Whichever are not important, they just remove, and then it tries to have a some architecture which retains the informations for longer. Logistic sigmoid function is commonly used as activation function. The sigmoid function is used. It can be stacked together to get stacked LSTM. Okay, so you can also use in LSTM like BLS, like LSTM, BLSTM. LSTM is short-term memory. Then you have this GRU network. It is also similar, but it is little less parameters, less LSTM scale. Okay, the first one will be the LSTM, then GRE, then RNN. But in RNN, if you modify with this bidirectional and then stack, then it can change. But usually with a simple single cell, RNN, its performance is not that good compared to LSTM or GRE. So that you are seeing, so how LSTM works. The great advantage that the LSTM provides of the RNN is that it prevents the loss of the long-term memory, which arises in the RNN because of the so. Okay, so whatever we have this difficulty, we see this explosion of these gradients and vanishing gradients. Those problems are taken care in this LSTMs. Okay, so you have actually a modified architecture that I was telling. So in LSTM, you have this you can say that these are actually two lines, long-term memory and short-term memory. Okay, so there are 4 gates are present: learning gate, forget, remember, and use. 4 different gates are there, which actually are different than your other. Okay, so basic principle is it will combine the previous information. Okay, the previous information will combine. So how actually it is modified, that we are going to discuss. So here let's consider that ET, okay, it is the informations. This is the full block of this long short-term memory. Okay, so you have this long-term memory and short-term memory. There are 2 blocks. X is the input. X is the input, and then EI is the previous information. Okay, it is the previous information. What it does, you have this sigmoid. Okay, it is combined, and you actually it's not X, it is actually a multiplications. Okay, and then you use these informations with the previous informations. From each states, you will get 2 informations: LTM T-1 and STM T-1. Okay, so these are combined. Okay, so now you have one present informations which is combined with these 2 channels, long-term memory and short-term memory. Long-term memory is also combined and short-term memory is also combined with these 4 different bits. So we have this 4 different, this learn gate. So learn gate, you have this STM. If we just see this STM T-1, what it does, you have this input which actually process the previous informations combined with this tanh. Okay, so whatever is the output, okay, so that's actually this tanh into Wn of STM-1 and ET. Okay, this is the present information, and STM is the previous HT-1. Okay, so and then plus bias. This is the HT tanh. Okay, and then you get and this total the output. And this information, present informations, are actually to have some ignoring factor, the sigma. Okay, so I1 is used with this sigmoid function of Wi STM, the same WST, this previous states, H means this outcome, and this present informations. You combine them using this sigmoid functions. Okay, so that's the ignored part, and this is connected. Okay, here. So you are using basically with tanh and with the sigmoid. Okay, so both informations combine, and then finally you get which is ni dot ii. Ni is you use this using tanh, and ii you receive using this sigmoid. It first takes the short-term memory and current input is the CI, combines them with a linear function and then apply tanh activation functions, and combines in a sigmoid activation. Okay, this is a sigmoid activation. This will determine which values to keep from this tanh output. So some informations it may avoid. Okay, so using this information multiplication functions. So finally, this STM and I minus 1, you will have these two information, NT and this II, okay, multiply. So similarly, you will have forget and remember get. Forget also, you will have from the previous state, you will have LTM and STM. Okay, so from the this present information sigma, okay, so you process and then give some sigmoid functions using the sigmoid functions, and then you connect with this long term in memory. Okay, so there are basically two memories, short term memory and long term memory. So long term memory is connected, you use this LTM minus 1 into FD. So this is actually processed in the as a forget get. And then remember get, this whatever you have this LTM t minus 1, you apply this forget get and you use this learning get both. Okay, combine them together and you receive this equation. Okay, so forget get first calculates a forget vector by combining short-term memory and current input in a sigmoid function. It then multiplies by the forget vector. The remember get simply updates the long-term memory as the sum of outputs from learn get and remember. And use gates are actually this is the information. Okay, so you see, okay, so I'm just saying that you also remember, but you do not need to understand also all this detail. These are little complex. Okay, so this gates information, how these are processed, but all are actually using this previous state information. Okay, so this the previous state information, whatever you have. So these are coming with these two memories. Okay, the same information first is coming with this long-term memory, another coming with the short-term memory, and they every time the short-term memory is modified. Okay, which we do not require to remember the long context past information, but long-term memory it will remember those past information. Okay, the use get remembers what the new short-term memory will be. First we combine the previous short-term and the current. Okay, so these are some details. Okay, but I do not want to go into these more details with this mathematics. Okay, so just I have explained. Okay, so you can read them or later somewhere you need to understand. Okay, so first you have to understand with this hands-on and then it will be clear. And then in LSTM versus GRU is a lighter mode of this LSTM. Okay, GRU is using has only one state where it can have both long term and short term. Okay, so it doesn't use actually both line. Okay, it uses only a single line. So it is computationally efficient, faster. Okay, but if you want to process, LSTM will give you better results. So if you want to go for more details of this GRU is having basically two gates, reset gate and update gate. So these are actually this architecture of this previous information. So you have this XT is this present information and HT minus 1 was the past information. You see this update gate and reset gate. Okay. So reset gate combines previous hidden state and current input with a linear function and then applies a sigmoid function. And update gate also combines the previous hidden state and current input with a linear function and then applies a sigmoid. So sigmoid function, however, the weights are and biases are different. So you remember this sigmoid functions and then this tanh functions. What is the difference? Okay. So sigmoid functions is actually giving you the outcome is always from 0 to 1. Okay, and then tanh will be minus 1 to 1. And if you are using this linear functions, so linear function is whatever you have this input, you actually give it propagates the same output. That is the linear functions. Whatever your input, you propagate the same. Okay, that is the x, y equal to x. Okay. And then if you reset combines previous hidden state and current input. Okay, so previous hidden state and this current input you combine and then applies with a linear functions and then applies a sigmoid activation functions. And update gate is actually you will have this, linear functions. So xt is multiplied with this ht minus 1. Okay, it is multiplications. Okay, the linear function and then applies a sigmoid and then after that it will apply a sigmoid function. So here is said gate will have some sigmoid function. Tan h c. Okay, so you will see this in hands-on and then you will understand that how actually these detailed gates are used. So when you run an application, so you what architecture you will be using, RNN, LSTM or GRE. So LSTM is having more parameters. Actually, it will give you better results usually. GRE is you having less parameters. So you have to use actually this like your different classification technology, deep learning, whether you use GRE, you can also use this different experiments with GRU, different LSTM, and see that which one is better, and then you choose. So let me go with some applications when this RNA. Okay, so you will see in the hands-on how actually this LSTM, DLSTM, this will be used for text classifications. Okay, so this will be very clear. So let me go with some applications where if you have some applications like this, series data, how you can process. So for example, you have this video. So you see this is actually I have taken from on temple from Tamil Nadu, okay, Tirunelveli. So this text from in Tamil, okay, and I am from Bengal, so I didn't understand this scripture. So you see this, it's handwritten, okay, and you do not find any software which actually can translate these kinds of words to some Bengali. So for example, I give a Tamil words and I want to recognize in Bengali. Okay, because there are so many scripts are there in India and we do not have any OCRs, okay, of this handwritten scripts. But if you consider, if you go to this Europe or China, Japan, okay, you will see several softwares they have developed so that if you do not understand, if you just use their app, you can understand, okay, what is written over there. So complexity in handwritten recognition is there. So if you, I think you might have, you are aware of this character, simple character recognition. Okay, it is very MDC data sets you have, and then you will have actually this, if you consider this word recognition that I was telling this, you have several cursive nature of text. Okay? So for example, foreign, guest, president, okay, all these words are there. So these are all in cursive. So if you want to recognize these words, because sometimes after P, it could be coming as pen, presidents, any other words. Okay. So how will you recognize? So you have to recognize with characters. You have to know these characters. If you want to recognize the characters, so where you will be segmenting. So if you want to recognize the character level, so you have to segment the characters. Means where is the R, where is the E, where is S. You have to segment those characters. Without segmentation, you cannot recognize. Okay. And for segmentation, you need to know that what is the character. If you want to segment this R, so you have to know that from where this R starts and where it ends. You have to know that it is R. Then only you can segment. So that means this is a chicken and egg problem. So if you want to go for segmentation, you need to know the label. If you want recognition. If you want to recognize, then you need to know segmentation. So if you want to recognize art, that means you need segmentation. So you have to have segmentation recognition both. Okay. So this is actually a typical problem in words. Okay, handwritten words. Similarly, in speech, everywhere when you are using this time series data like this, word recognition, speech recognition, so you have a set of characters or set of phonemes which come one after another, which you cannot segment. Okay, and without segmentation, you cannot recognize. Okay, so this is the point. So you see this complexity will be simple characters. You have this full words, and from full words you have a sentence. For sentence you require natural language processing. So one sentence, how actually this second sentence appear? What is the influence? Okay, and then if I'm going for this Indian text context, you have this Indian characters, single isolated characters, then Indian word, Indic word, which comes with more number of characters. Okay, so it will not having 50 letters. Okay, it could have, because of your compound characters, it could actually go to a huge number of classes, maybe 400 or 800, something like this. Okay, lots of number of class. So then when you have huge number of class, then recognition is problem. Then similarly, you can consider this sentence. And when we are going in sentence in India, so sometimes one can write in Hindi fully, sometimes one can write some English words as well. So first, if you want to recognize using some computer, so it has to know that whether this word is English or Hindi. Okay, so because otherwise you have to use both scripts together. So Hindi, English, both late characters need to be trained together. Okay, that is more challenging. So this is the complexity. And then if we want to recognize them, so what actually people are doing? Okay, so there is actually work of convolution, conv recurrent neural network, okay, which was developed in 2017 for these kinds of character sequence recognitions. Okay, so for example, it could be a handwritten character or sequence of characters. How will you recognize it? So here, why it comes a sequence? Because the image, it could be a single character, it could be a long character, a sequence, a sequence of 3 or 4 characters. So how will you go for recognitions? So you can see that I can extract some small levels, like a small patches. Okay, so I can consider a small patch, and these are all features. Okay? So what we are doing, so we are using some convolution, CNN, okay, like this. Okay, input using convolution, max pooling, all this for full image, and then finally we have these features. These features we can consider them as a vertical way. We place them as an input. Okay, this is the first frame features, second column features, third column features. Okay, like this, you can consider first column features, second column features, third column features. If you have 100 column, then 100 column feature sequence you have. So this feature sequence we can use in a RNN, LSTM, or DLSTM. Okay, so this is the feature sequence, and we want to recognize them in a we want to recognize what are the character sequence appears. It could be a state, it could be so, it could be statement. Okay, what will be the sequence of it? So we have these features, one x1. See, for example, you have this one columns, you could have 100 features, for example. So x1 to x100. So x1 to x100, you fit into this block and you get the some results. You see that, okay, maybe the result is yes. Same, this information is coming for the second sequence and the previous layers block, and then you recognize, then you say that, okay, it will be same letter or it is nothing planned. Then it will be next one sequence of features is says that it is P. So like this, actually, you recognize those characters from this given sequence of features, which are extracted from this image using convolution neural network. You see here, these convolutions, CNN, RNN are coupled. Okay? CNN extracts the low-level features, okay, the features, okay, so which are used for recognition of a single image. But as we are not able to recognize a single because it's not possible to segment, right? So that's why we are using RNN, okay, because it's a sequence. So when it's a sequence, we use this RNN for recognition. So it will give you a sequence state. So these codes are all available. Okay, so this is not my paper. This is actually a standard Fermi papers in 2017. So what they are doing, you have a width of 32 grayscale image, and then you use convolution max pooling like this. These are the layers, and then finally you have these kinds of feature maps. So these feature maps you use bidirectional LSTM 2 times. You see here BLSTM 2 times. It's a stacked BLSTM, and then you get the results. Okay. So then you can say that, okay, what is the what people are doing now in this text recognitions. So people are now actually working on style transfer. So machine can actually understand that what is your pattern, how actually you write. So for example, you see this, if you give some examples of this text, then machine actually generates this sequence. These are the strokes generated by machine. Okay, so how you write? So you see that these kinds of strokes, okay, this look like human, but these are all generated by machines. Means this one pixels to another pixels, how this pen will move, these informations actually come through this RNN, okay, this DLSTM layers, okay, generating sequence with recurrent neural network. So these are all applications of RNN. So you are generating, okay, generating the the how the sequence of pixels, how you will write. So then you can have the other works like activity recognitions. Activity recognition, for example, this it's a single action. Okay, single action, but it's a frames, a set of frames. Okay, so if you want to go for recognitions, you have actually, for example, you have 5 frames. So each frame, if you give a single frame, you may not recognize what is the level, but you have to use the context information of all these 5 levels. Then only you will understand that, okay, she is doing some exercise. From these 2 persons, with a single frame, you will not able to understand what is doing. But you will see that if you are making some frame analysis, this every frame, what is actually happening, then you can analyze all these activities. Similarly for this group work, okay, so this action recognitions. Okay, so multiple people they are working together. Okay, so these are more complex problems in action recognitions. So either you can use for this action recognition using a simple camera, or many people are actually using some Kinect, okay, Microsoft Kinect, which actually provides this junction points of the human. So if you use this Microsoft Kinect here instead of camera, so you will get the stick diagrams like this, okay? Like human body, like this stick diagrams. Okay, so you will have this. You will not do not need to work with this image. So in image, actually, you have to detect where is the face, where is the hands, all those. But with this Kinect, it actually gives you there is an inbuilt GUI which provides you these stick diagrams. Okay, all these junction points. So from these junction points, you can understand that, okay, so what activities they are doing. So you do not need to work with these pixel levels here. You will use only with this 20 junction points. So for example, for each persons, you will get 20 points. For example, head, neck, okay, left hand, right hand, left leg. Okay, so these are the points, junction points it will provide. So if you move, those junction points will only move. So you need to process only those junction points. Okay, how these points are moving. That means this is actually a trajectory. This is actually a sequence of pixels, or you can say that sequence flow of those junction points. So given this flow of these junction points, can you recognize the action? So it could be possible in indoor games, like for example, if you want to do for two-person interactions. Okay, so two persons in ATM. ATM, if there are two persons, they are actually doing some fighting together, or they are friendly. Okay, so how you want to monitor them? Okay, so what activities they are doing? So for example, they are doing boxing, dancing, jumping. So these kinds of exercise, these kinds of different activities, group activities are there. And then you use the Microsoft Kinect, and these are the stick diagrams, the junction points. And from those junction points, you can use this RNA and LSTM. Okay, these are the sequence of this time frames. Just each frame you get 20 points. Second frame you get a set of 20 points, 20 features, which are little change. Okay, so you are actually finding this, for example, 100 frames. In 100 frames, 20 features in each frames, and you get the combined result. Okay, you make this RNA and LSTM, and then you see the results. So like this, you will have the stick diagrams like that, and you can get the result. This is actually done for this gate recognition. So sometimes you want to know that with this from this gate or just posture, you want to know that who is the person. It could be used for biometric. Okay, so you want to know that who is that person. Okay. And so these are some other works. I just don't want to go. So this is actually sign language. You can also use sign language recognition. Sign language recognitions. You see, this is actually a lip motion. It's a sensor. This is done in our lab. So we are making some gestures, and this sensor comes with this GUI, and this gives you this point, junction points. Okay, so you see this junction points. So when he moves, this actually comes with some junction points of fingers and palm. This we do not generate. This comes from this device. Okay, so you do not need to work. So finally, what we are getting input is only those junction points. Okay, this what are the points, and you see this. We analyze only these trajectories, the movements of these fingers. Okay, so for example, this character recognitions, word recognition, cursive natures. Okay, how this um, pixels are moving. Okay, from one point to another frame. So similarly, here it is in action also, like the junction points of head, how it is moving. Here we are saying this finger junction points, how these movements are done, how this junction points of fingers and palms are moving. So when we have these movements are actually a path. Okay, these junction points, these are actually continuous. Okay, this time series data. Okay, this is a time series data. Okay, so for example, you have 10 inputs, 10 in or 20, 10 inputs or 20 inputs according to the number of junctions, and those junctions are giving you data in each frame, and then you process them, and finally you have the labels. Okay, the label is the gesture meaning, whether it is a color, whether it's a name, or whatever. Okay, so we are doing it using LSTM, DLSTM, RNN. Okay, so you consider this RNN or LSTM for finding the features in each frame, and those frame and context information are combined together to have the final level results. Okay, so sign language, actually you have usually sign language people are working with simple image. You can use, for example, a single word level that I have explained. I have shown you the video for a single word, how actually you want to make it a recognition of the single gesture, like word recognition. That for example, OCR, character recognition, it's a simple character. It's a gesture, full word recognition. And if you want to go for this full sentence, actually, so that's actually more complex. and people, I don't think there are softwares which actually can work for this full phrase. Okay, so which actually require your LSTM, BLSTM, all this. Okay, so for a better model. So you actually, this guy is using a full sentence. So can we use this models for translating these gestures into a Hindi, English, or any language? So there actually you have to use this many to one and then one to many that I explained. Many to one means you have from each frame you get some features, and those features, from those features you get the meaning, and that meaning you use in a one to many for a English sentence, text level sentence or Hindi level sentence. Okay, so any comments, anyone? Otherwise, this is another work that we are doing. We are also working on brain-computer interface. Okay, so you see this brain-computer interface. This is a head scalp device that is putting some gels. Okay, so that it's actually connected those electrodes, and there also it's these electrodes are, if these are active, then this will actually be green, otherwise this will be red. Okay, and then it's also a time series data. Okay, so in every frame it's like ECG data or ECG, it is called electroencephalogram. Okay, it is like your heart data. So it comes with some signals. Okay, signals will be of some waveforms. So for example, you have these kinds of waveforms. Okay? So if you want to analyze that what is the disease of that person, or for example, what emotion of this person, okay, so we can actually understand from this EEG. So for example, this guy is making some blinking. So one guy, the user was asked to blink, and then we actually record from this EEG thing. See this the pattern. And when he is blinking, you see there is actually change of pattern. Okay, this time series data, you have change of pattern. Okay, this is the when he is not blinking and when he is blinking. So you see this, these are all time series data, and from one frame you cannot actually get the full cluster. So you require set of frames, okay, 100 frames or 50 frames, and you see this what is the amplitude, and these are the features. And from this you have to analyze using RNA and LSTM, LSTM, and you. So usually we use all this deep learning of this time series data, LSTM, LSTM. Okay. So for example, if I'm giving you an age and gender recognitions using EEG or anything, any problems of this EEG data. So we will have these EEG data sets from some people. So like that, we from 60 individuals we collect the data from EEG data, EEG signals, and these are the, for example, 6 to 10 years as a class 1, 12 to 15 years class 2, like this, different age groups, different gender groups. Okay, and then we have a data set of this training data. We make some few models with this from using this LSTM, DLSTM, and then given a test data, we process using this model and get the results, that what is the age or what is the gender. So we use this architecture like this deep learning architecture. Pre-process, for example, you have this EEG layer. We use BLSTM layer. We use some dropouts. Dropouts, I think you know this dropout is just to remove some of the weights which are actually some nodes which are not important, and then some normalizations, then LSTM layer, then normalization, then LSTM layer. Then so you have this BLSTM, LSTM, all this okay together, and finally we make some predictions. So you see here we are considering a stack. Okay, LSTM, BLSTM together. So you can use all these combinations, BLSTM, bidirectional, you can use LSTM sometimes. So you have try with the different permutations, you see that which actually work. So if we are using with simple LSTM, is our results will actually see that we got 96.35 for gender and age is 88.35, okay, something, or 89.5. Okay, so with one band. I'm not going into details, but if we are using BLSTM, here BLSTM didn't provide better results. But if you are using LSTM, BLSTM together, so we got a little higher accuracy, okay, than this LSTM, BLSTM. So you see the results are actually better. So like this, actually you have to trial and error. Okay, so which architecture is better? So I have shown you several applications, and there are many possibilities. Okay, natural language processing, music generation. So for example, I have one video. So let me show you. Video I have. Yeah. So you see this video. So this is a silent motion. Sounds are generated. Okay? Sounds are generated by. So you have a video. So it understands the material first. Okay? So you got the idea. Then this music generation, sound generation, sentiment classification, speech recognition, machine translation, weather forecast, everywhere actually you will use this time series data analysis, deep learning. Okay, so thanks. Yeah, if you have any comments, doubts, you can discuss. Okay.
No, sir.
So you will see in the other half, other sessions, these practicals. Okay, so how actually this text is processed, and you get the results using these three different architectures: RNN, LSTM, GRU. Okay, so with these three different architectures, how what are the performance you get? Okay, so how you can modify all those stuffs you can see. Yes. Okay, thank you, Dr. Virendra.
Thank you, sir. Thank you. So
Yes.
we will meet then at 2:30, sir.
Yes.
Yeah.
Thank you, sir.
Yeah, if anyone having any comments or doubts, yeah, you can discuss with me, or
Yeah.
maybe
So
add some.
participants, like if you have any queries, like you can just ask. Or if you have any queries with respect to the data or any project that you are working on, so with respect to that also you can ask. Okay, so if there are no further queries, then yes, sir. So we will meet at 2:30, sir.
Yes, we'll meet at 2:30. So one of my student, actually Anmol, he will be taking. I'll be there. Okay. So he will
Okay,
be
okay,
taking this
okay,
hands-on. I have given him
okay.
this link,
Link.
and he'll be there. Yes, everything.
Okay, okay, sir.
Thank you very much. Thank you.
Okay, thank you, thank you, thank you.
Thank you, sir.
Thank you.
Thank you, all participants. Thank you.
Thank you.
Thank you, sir.
Thank you very much. Thank you. Thank you all of you.